So in this video, we're going to wrap up our application of acid-base chemistry by looking at this clinical scenario, and it's taken from the American Journal of Pharmaceutical Education and from this specific article about improving pharmacy students' understanding of acid-base chemistry. I'll post the link of the article. It's interesting to look through to help solidify your acid-base knowledge if you're looking for more sample problems that are more clinical or more real life type situations. So the scenario is that you have a patient that has overdosed on phenobarbital. And we know that phenobarbital is an unionized acid with a pKa of 7.4. The patient's urinary pH is given as 5.4. Ideally, should we want to increase or decrease the acidity of the patient's urine in order to help save this patient, okay? So in the last video, we did talk about how we see two main functional groups here, two amides, pKa is 8 to 10, around 8 to 10, but we see here that the exact pKa of phenobarbital is actually 7.4, and the patient's urinary pH is 5.4. So we want to know, is it a better idea to increase or decrease the acidity of the patient's urine? So in other words, do we want the pH to be, for example, 4.4, where we decrease the pH of the urine, or do we want the pH to be higher than 5.4, like 6.4? Which of these two pHs for the patient's urine would actually help the patient get rid of this drug and help them with their overdose? So in order to answer this, you do need some background knowledge. You need to understand that the unionized or the ionized form is the excretable form. So that's the first thing you want to understand for background knowledge. You want to know, is the unionized form or the ionized form the excretable form? And the answer is that the ionized form is going to be the excretable form for phenobarbital, okay? And this is going to make more sense later when you start to learn about pharmacokinetics and excretion and tying in acidity and basicity there. But for now, all you need to know is that the ionized form is the excretable form. So in other words, the ionized form is the form that would allow the patient to get rid of the drug more quickly and would be a better idea for the patient who has overdosed on phenobarbital. So now we want to know, should we lower the pH to 4.4 or should we increase the pH to 6.4 of the urine in order to produce more of the ionized form of phenobarbital and thus the readily excretable form of phenobarbital? So what you could do is you could look at this conceptually, or you can do the Henderson-Hasselbalch equation a couple of times. So the way I chose to solve this is I first started with the Henderson-Hasselbalch equation for the pH of 4.4, and then, the original pH given, which is the pH of 5.4. And then I solved the ratio for pH 4.4 if we were to reduce the pH, and then I did the problem a third time with pH of 6.4. So this is the option of decreasing the urine pH, this is increasing the urine pH, and then this 5.4 is just your starting point for comparison's sake. So pH of 5.4. So again, we're starting with an unionized acid. So the form of the equation we need is pH minus pKa equals log of base over acid. But because we have an unionized acid, the unionized goes on the bottom, and then ionized form on top, and then it's always base over acid. So this is the formula I'm going to use. The pH is 5.4. The pKa that we were given is 7.4. So pH of 5.4 minus 7.4, and then we're going to continue solving this. So 5.4 minus 7.4 is going to be negative 2. I'm just going to skip to that step. And then we have log of ionized over unionized. And so I have 10 to the negative 2 equals ionized over unionized, 1 over 100. I rewrite that, ionized over unionized. So I have 1 ionized to 100 unionized. So that's for the first one, just for reference. So we are primarily unionized. So now what happens when we decrease the pH? So now we're going to do pH minus pKa equals log of IB over UA. And so 4.4 is the pH, and now that we've changed it, and the pKa is still 7.4. So 4.4 minus 7.4 is negative 3. So that equals log of ionized over unionized. And then that's going to be 10 to the negative 3, or 1 over 1,000, ionized over unionized. And so what we've seen is we've actually here we've increased the amount of unionized compared to our starting point. Our starting point we had 100. Now we're going up to 1,000. So we're, in this scenario, we've actually increased the amount of unionized form. And that's not the goal. For the patient to get rid of phenobarbital in this clinical scenario, they would need to have more of the ionized form. So I'm already kind of skeptical about this first option. I feel like this is not a good option. But just in case, I'm going to continue. pH minus pKa equals a log of the IB form over the UA form. So I'll just put ionized over unionized. And so the pH in this case, we're changing to 6.4. The pKa is still 7.4, so 6.4 minus 7.4 is going to be negative 1 equals log of ionized over unionized. So we have 10 to the negative 1, which is the same thing as 1 over 10, ionized to unionized. And so we actually, in this scenario, compared to our baseline, we've actually decreased the amount of unionized. Right? So having 1 to 10, well, now we have less unionized because 1 to 10 is ionized to unionized. And then here we started with 1 to 100, where the 1 was ionized and the 100 was unionized. Here we had 1 ionized, 10 unionized. And so just by looking at these numbers, I can conclude that the answer should be to increase the pH of the patient's urine so that we can decrease the amount of unionized, and by default that means we're increasing the ionized form so the patient can get rid of it. And then I thought that this would actually be an easier problem if you just did percent ionization. So percent ionization, you would do the 1 ionized divided by the total 1 over 100. So you put your ionized on top. And so that would be 1 over 101. Here you would have 1 over, so the ionized is 1, and then the total is 1,001. And then you can get your percent ionized there. And then here you have 1 over 11, and you can 11 because it's 1 plus 10. And so then you can get your percent ionized there. So remember, you're always putting the ionized in the numerator and then dividing by the total, 1 plus 10 or 1 plus 1,000 or 1 plus 100 to get your percent ionization. So you can pause the video now and start calculating these percentages. So ideally we want the highest percent ionized. All right, and so for that first question, 1 divided by 101, you'll have 99%. Oh, I'm sorry. So if you do 1 divided by 101, you'll get 0.99%. So that is the percent ionized form, 0.99. Then in this next example, 1 divided by 1001, and then to get that percentage, you would actually get 0.099% ionized. So you've actually decreased the amount ionized. And then for that last example, 1 divided by 1 plus 10, or 1 divided by 11, the percent ionized is actually going to be around 10% or 9%. So by looking at the percentages, this is the percent ionized. So we want to pick the largest percentage, which is 10%. We started with 0.99%. So increasing the percent ionized, in order to do that, we would have to increase the patient's the pH, the pH of the patient's urine, and that would cause the patient to have more of the ionized form and to be able to get rid of the drug more quickly. So that's just a fun clinical example to consider, or more like a real life clinical example. Whether or not this will happen in reality, I don't know if you'd ever solve a clinical question just based on acid-base chemistry, but it's just interesting to apply everything you've been learning.